Quick comment on example 1 before we really get into this video. First off, this is not a typo. I just don't know Washington Rivers very well. This is actually what it's called. And second off, I found this from Google, but you may or may not know that different months have different numbers of days. We should have checked it for October. So the number is slightly wrong, but the idea is still the same. October has 30 days. This number up here, I do not think is for 30 days. But that's the idea. Anyway, let's talk about something called a definite integral. Chapter 3 is all about integrals. We're going to start by talking about one kind of integral. Yes, there are different kinds of integrals, but don't worry, it's actually not. They're pretty much the same. We'll start by talking about the definite integral. We won't talk about indefinite integrals until a future section. So I've mentioned that, okay, area under a rate of change gives the total. And that area is a definite integral. So we found this in a couple of different ways. Right, this blue area is an integral. And before, right, we found it using geometry here. Or we approximated with geometry here. But we're trying to figure out a better way of doing it. And this looks like not a better way, but if it's a very common way, it's called the Riemann sum method, is we can actually just use a bunch of rectangles to split it up. And you might say triangles should work better than rectangles. Why are we using rectangles? Well, basically rectangles are easier. And it turns out it won't matter which one's better. They're actually mathematically basically the same. In the limit, using that concept of limits again, as we get more and more rectangles, I'm going to show you something that's really cool, really cool. I'm very excited, visually happy as well. So let's visualize, ignore all this stuff on the left. Don't just look at the picture. Just look at the graph on Desmos, okay? So we can see a bunch of rectangles. Let's focus mostly on these purple rectangles right here, okay? We are estimating the area under the curve with these purple rectangles. Now this estimation is garbage, right? Well, we're using rectangles. There are better ways of approximating this, but let's put a couple more rectangles in. Now that we have more rectangles, still pretty bad approximation, right? We're missing all this area here. We're over counting over here. Not so great. Let's add a couple more rectangles. A little better. Some more rectangles. A little better. More rectangles. More rectangles. More rectangles. Look how good it's getting. 100 rectangles. What about 1,000 rectangles? 200 rectangles, 300 rectangles. We're still undercounting here a little bit, and we're still overcounting here. 400 rectangles, 500 rectangles. Eventually, notice, we're really going to get that area. So that's pretty cool. Now, you might say, Jason, I hope you're not expecting us to add up 500 rectangles. Don't worry, I'm not. What are we looking at? We are looking at the limit as the number of rectangles goes to infinity. That concept of a limit in calculus. Infinitely many rectangles, each is infinitely thin, is going to give us that area. Now there's some really cool theory going on behind the scenes that we're not going to talk about. And you can actually do this without any calculus at all. Just set up a formula for these and then take the limit. Oh, that's calculus. No integrals at all. You can take the limit of these Riemann sums and really get the precise exact area. But we're skipping that. We're more application focused. But that's kind of what's going on. This idea of a Riemann sum, approximating this area with rectangles. If we have enough rectangles, we get the exact area. Well, we need infinitely many, but then we'll get the exact area. And we're finally to the definition of a definite integral. Okay? And I'm not going too precise. The book has like a full page definition of this. I kid you not. I think it takes up an entire page. Let's just take some of that out. You have a book. You can look at it if you want. And basically, if you have infinitely many rectangles, you get this Riemann sum, this definite integral, sorry. So the definite integral, when I say definite integral, what do I mean? The definite integral of a positive function over some interval is the area under the curve from the start to the end. And this is how we write it, okay? This is how we write a definite integral. You may have seen this integral sign before. So we got a lot of things to label here. Again, this right here is the integral sign. A and B are the start and the finish. They're collectively called limits of integration. The function on the inside is what's called the integrand. If you have a radical, like a square root, the inside of the square root is called the radicand. This is the same idea. The inside of the integral is the integrand. And again, one more thing is that A and B together, I'm running out of arrows. A and B together are both called the limits of integration. This is what an integral looks like. This is how we write it, and it just means the area under the curve of that positive function. And then more formally, kind of what we said in the last video, if f is a rate, then the definite integral is the total change in that interval. So the total change in flow, the total change in distance from that car. That's what we've got here. Let's use that in one example here, and then in 2 or 3 more examples in the next video. So the graph below shows some function. Y is some function r of t. And this function shows the number of telephone calls made per hour on a Tuesday. I don't know. Maybe it's telephone calls made by, I don't know, a call center or a company or an ex-boyfriend. I don't know. But how many calls per hour shown on this graph? So again, this is a rate. The area under the curve of a rate gives the total amount. All right. So approximately how many calls were made between 9 p.m. and 11 p.m.? And there's a couple of ways of doing this, right? At 9 p.m., there was about 100 calls per hour. At 10 p.m., there was about 170 calls per hour. At 11 p.m., there was about 200 calls per hour. We can use this information to estimate, right? Well, if at 9 p.m. there were 100 calls per hour, right? Well, then how many do we think there were between 9 and 10? 100. Right? And at 10 p.m., we said there was about 170 calls per hour. So in that hour from 10 to 11, we assume about 170. So we can just make a little guess and say we can approximate about 270 calls per hour, or calls in those 2 hours. That's not calculus. No calculus. Just using what we know about how numbers work. But what we are really doing here is a Riemann sum. Because it's not fair to say that there were only 100 calls between 9 and 10. That was approximately the rate at 9 p.m., but notice that between 9 and 10, the rate's increasing. So actually, there's going to be more than this. What we did is we found the area of this rectangle. We are undercounting the calls. There's all this area that we're not taking into account. And then similarly, from 10 to 11, we assumed that there'd be about 170. We're finding the area of this rectangle. And again, we're missing all of this other area, so we're undercounting again. But we were just asked to approximate with a Riemann sum using two rectangles. And that's exactly what we did. How do we write this as a definite integral? Let's go back to our definition. This is what a definite integral looks like. And it is the area under the curve of a function from a to b. So, the area under the curve of the function between 9 and 11. What's our function? R of t. I forgot to give you one piece of information on the last page. It's very important. You may have been wondering about it. What the heck does that dx mean? Well, you've seen dx before, right? Derivatives. We saw dx. We said dy dx. What did that mean? That meant derivative of y with respect to x. It's telling you that x is your variable. Well, this is the same thing. This dx right here says that we're taking the integral with respect to x. So you can write with respect to x if you want, but what that really means is it means x is our variable. And you might say that's not important, but it really is. Because what if we try to take the integral of a quadratic, any quadratic, from like 1 to 2 or something? Well, this integral is going to be very different from this integral. A could be our variable, B could be our variable, C could be our variable, X could be our variable. We have to say what our variable actually is. There's a couple other interpretations. No need to erase that, I guess. There's a couple other interpretations of dx. This is the simplest interpretation. It just means that x is our variable. For us, anyway. It also just means dx is also like a really, really infinitely tiny width. And the function value is the height. So that's what we have here at the end. Not dx. X is not our variable. What is our variable? It's also not r. Our variable is time, t. So this integral, this definite integral, is the area under the curve, which we don't know. Even I can't figure this out because I don't have the function. But we can approximate it with the number 270. And that's what we'll spend the next video doing. Get more practice. How do we evaluate and approximate with rectangles? And again, that's not the only way to approximate. And how do we write that with that integral notation? Let's get practice with this integral notation for what it means and how to write it, so that in the future, when we're calculating it, it's a little bit easier to understand. Good luck. See you next time.